you will find that it's really easy, right? So let's start. Let's look at 1 qubit. For 1 qubit case, we don't have tensor product because this is the smallest, lowest dimension we can have for qubit, right? What is the general expression of a qubit? Psi equal to alpha 0 plus beta 1, correct? Because it has 2 basis states, and I can write it as alpha beta, 2 basis vector. Now, how about 2 qubits? Now you will see that a 2 qubit state can be expressed as a tensor product of the lower qubit. For example, let's just look at this. Psi, you can say it is just equal to summation j equals to 0 n minus 1. I'm just copying the equation I had earlier. dj alpha j. Remember this? Right? In the 2 qubit states, it can be expressed as the combination of the lower one. But here, of course, n equal to 2, right? So I only have F0 tensor product G0. Is it n equal to 2? No, I want to make, it doesn't matter actually, sorry. It depends on how many you want to combine. Actually, I want to give an example that is n equal to 1. So it only have one term, okay? For example, n equal to 1. So it's F0 tensor product 0, for example. Okay? So I'm going to say F0 equals to alpha 0, right? I'm going to put this 1 plus beta 0. I'm going to put this 1. Tensor product gamma 0. I put 2 plus beta. I did something wrong here. Sorry, this should be 1. Right? Beta 1. 1, 2. Do you understand what I'm talking about here? Does this make sense to you? A tensor product of 2 vectors from a 1 qubit state. The first 1 qubit is alpha 0, beta 1. The second qubit is gamma 0 and should be delta 1, sorry. Is this okay? Why do I put 1 and 2 as the subscript? What does it mean? The first space and the second space, maybe the first electron, second electron, first ion, trap ion, second trap ion, right? So this is from this, I don't call it second space, let's just call it H. H1, this is H2. Is this okay? Now we just learned that tensor product follow what? All the distribution rule, right? So I can treat it like what I did for the multiplication, right? So this one, if I do it, it is like this. See if you agree. It becomes alpha, gamma, 0, 1, tensor product 0, 2. Plus alpha, delta, 0, 1, tensor product 1, 2, plus beta, 1, 1, times gamma, 0, 2, plus beta, delta, 1, 1, tensor product 1, 2. I missed the tensor product here. Is this okay? What I'm doing is just like regular multiplication. Why can I do that? Because I already show you this equation, the distribution law, right? So I can do alpha times gamma, 0, 1, 0, 2, alpha times beta, 0, 1, 1, 2. Beta times gamma, 1, 1, 0, 2. Beta times gamma, 1, 1, beta times delta, 1, 1, 1, 2. Is this okay? Right? I show you those difficult equations first because this one you can understand easily, just like how you do multiplication. Why is so easy? Because of the equation I showed you earlier. That is just the property of the tensor product. Now, if I say this is 0, 1 tensor product 0, 2, would that be a problem if I rewrite it in this way? Will you feel confused, unhappy? Should I take away a point from you in the exam if you don't write the tensor product? Simple. I should never take what? Sorry, my ears. Oh, okay. I'll give you 100 points. Just kidding. Okay, it's recorded, my God. Is it okay? Do you think it's a problem? Exactly. Do they mean the same thing? They do, huh? Yes. In this class, right? In quantum computing. Because we all know that when we write two vectors next to each other, it cannot be inner product, it cannot be outer product. There's no other thing, only tensor product. So I will ignore this one, right? What if I write it in this way? Is this okay? Yeah? Now this time I'm not going to ask you about the exam. It's okay, right? Because we already know that the first one is the first electron, second one is the second electron. We already know that, but you don't lie to yourself. If you're going to swap it, you better look at it carefully. Otherwise, it's the same. How about this one? Would that be a problem? Yes. And they do mean the same thing. Yeah? Because you're already familiar with this. 0, 0 just means that I have a basis state formed by the 0 of the first space and the 0 of the second space. And we combine them. Now you see that the basis states expand from 0 and 1 to 0, 0, 0, 1, 1, 0, and 1, 1, right? Yeah. Yeah, good.
If these two are swapped, if I rewrite this by swapping these two guys,
Yeah. If you only swap these two guys, then you are incorrect. But if you swap every of them and tell us that the first qubit is this one, then it's correct.
if we had put the subscript, then there would be so like in this line, since you have taken away
1 and 2.
subscript,
Yeah.
then there's a danger.
There is a danger. You are right.
But if you had these one and two, then it'd be clear that it's
Correct. Correct. But then after that, it really doesn't matter which one is called 1, which one is called 2. When you do the operation. Think about this. It's just like the physics. I have two electrons, one put on the left, one put on the right, right? The physics is there. If I go to the other side of the table, the 2 is on my left. You should have the same result, the quantum computer. Correct? If I always label left one is 1, right one is 2, right? On this side of table, I get this one left. the left one is 1. I go to, and from your perspective, your left one is actually 2. But we should get the same quantum computing result. So as long as you're consistent, the results will be the same. Okay? So, but do not only swap one of them, then it is wrong. Good question. Yes. If you reorder it, you do reorder it. But in all your derivation, you need to keep the same order. You always have the 2 in front. Then eventually you get the same result. Yeah. Now,
Do the coefficients need to be
then you don't, because they're just number.
Yeah.
So alpha times gamma equal to gamma times alpha. So if you're okay with this, how about this? Would it be confusing? If we all agree that which one is the first qubit, and you agree that we are the intelligent who know decimal number, and 3 means 1, 1, then it's not confusing. Okay? I try to write the basis as 3. Again, it's in the cat notation. I can write English 3, THREE, Japanese or French, whatever. I'm still referring to the same thing, the 4th basis in this larger space. And this 4th basis is formed by the 2nd basis of these 2 subspaces. And this one, if we try to write in the column form, it becomes alpha gamma, alpha delta, beta gamma, beta delta. The first one say we have so much component of the first basis, so much component of the second basis, so much component of the third basis, and so much component of the 4th basis, right? Which is 1, 1. Is that okay? So these are all just psychology. You actually can master them very well. If you teach this to a kindergartner or maybe a first grader, second grader, they won't feel difficult because it's the same as regular multiplication distribution law, multiplication and addition. You just change the symbol to this one. Okay? Okay, so we know how to find the tensor product of qubit. I give you 2 qubit. All you need to do is just multiply that. Let's look at a higher dimension, right? So let's look at the power of quantum computing. So let's look at the number of electrons. If I have a 1 electron, how many bases does it have? How many bases? Vector? 2. We have 2, right? And what are they? Thank you. I'm going to call it 0 and 1. Again, it's just a name. And we call this a C2 space, complex number 2-dimensional space, 2D complex space. Okay. Now, if I have 2 electrons, how many basis vector do I have based on what we just said? 4. And it is actually 2 to the power 2 equal to 4. Because you do the permutation, now is where you have the permutation. Do you see that? I permutate 0, 0, 0, 1, 1, 0, 1, 1. I got these 4 bases, right? How many basis vector? What are the basis vector? What are they? Yes. 0, 0, 0, 1, 1, 0, 1, 1, and just like what you said, which are 0, 1, 2, 3. That's why will it be confusing to see 0? It will. If it doesn't know that you are working on a 2 electron basis, you thought that it is this 0 basis, right? It will be confusing. You need to be very clear. You know the system, what system you are working on, right? We call this what? It's a C2 space tensor product with a C2 space, which is equal to C to the power 2 to the power C2 to the power 2, which is C4 space. Okay? What if I have 3 qubits? How many basis vector do I have? Permutation, right? 8, right? You have 2. If you are not sure, you can go home, just do the permutation. 2 to the power 3 equals to 8. What do we have? Now I'm going to, I will write it in this way. 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1, correct? Which are 0 in decimal 1 all the way to 7. So what space is this? It's C2 tensor product C2 tensor product C2 equal to C to the power 3 equal to C8. So our space is expanding by adding one more qubit. The basis vector becomes 8, 2 to the power 3, right? So in general, if I have n qubits, how many basis vector do I have? Thank you. 2 to the power n. Remember our example in the first class, I have 300 electrons. I have 2 to the power 300 basis states. What are the basis vector? Excellent. 0, 1, all the way to 2 to the power n minus 1. And you know very well now, this one means the decimal, right? If you want to convert to binary, you have 1, 1, all the way to 1. You have n of them. You have n1. So what space is this? Can you guess? C2 to the power n. Okay. Now, very important. Once we have this space, a vector, a general vector in this space equals to the linear combination of its basis vector, which is equal to A0 times 0 plus A1 times 1 all the way to an minus 1 times 2 to the power n minus 1. No, not an minus 1, a to the power n minus 1, right? Now you see the space is really large, just like we said in the first lecture. Okay, so that is how you form the tensor product. Okay, I give you 1 minute to copy, and then the rest is just some skill, how to do tensor product. Again, they are really, really easy, right? I will go through pretty fast, but very easy, right? You look at the difficult math, just to show you that we are building on very solid foundation. And now we understand how we expand to larger space when you have more qubits. Start with 2-dimensional to 4-dimensional, 8-dimensional to the power n. Okay, so let's move forward. Let's look at an example. This one I make it lengthy, but it's not a problem for you. For example, I have a vector in the H1 space. Which is V equals to V0 all the way to Vn minus 1, right? What does it mean? It means that it is V0 times E0 plus V1 times E1 plus all the way to Vn minus 1, En minus 1. What are these E0 and En? What are they? Basis vectors, right? So what dimension is this? N dimension. This is an ND vector. I have another vector in the H2 space, and it is this. W equals to W0 all the way to Wm minus 1, which means it is W0 times, let me call it F0, plus W1, F1, plus all the way to Wm minus 1, Fm minus 1. What dimension is this? M, right? I have M basis vector, MD. I can do tensor products with two bases that doesn't have two subspace that has a smaller space that has different dimension. Makes sense. I can have one qubit tensor product with two qubit, right? The two qubit already form a C4 space. I add one more qubit, it becomes a C2 tensor product, a C4 space. It becomes a C8 space. Or you can think of one qubit tensor product, one qubit tensor one qubit is also C8. Okay, how do we do the tensor product? Think about this. I can say V tensor product W. I just need to write them out. Tensor product, the whole thing, W0, F0, Wm minus 1, Fm minus 1. Is this okay? I just do the substitution. And then you just do whatever you do in the distribution law, right? What would this be? First, I do V0 and W0. I say this is V0, W0, E0, F0. I did not write the tensor product symbol, but you know that it is tensor product. Then I do the other term, V0, E0, no. V0, W1, E0, F1. Right? The first time I do V0 times W0, E0, F0 tensor product. Now I do V0 times the second one, I did not write it, W1, and then E0 times F1. I will repeat this one until V0, Wm minus 1, E0, Fm minus 1. Okay? Do the last one, V0, Wm minus 1, right? And then I do the second term, right? I do the second term, which is V1, W0, E1, F0. And then I continue until the end. I will do the last term, Vn minus 1, Wm minus 1, En minus 1. And then Fm minus 1. Say again? Where E1? N minus 1. Okay, I already finished this. I finished V1, V2, now I'm doing Vn minus 1 times Wm minus 1. This is the very last term, good point, yeah. What is the dimension of this space now when I do the tensor product? N times m. It's just permutation, right? Because for each n, each here, I have m of this, each of this, m of this, so I have n of this, so it is just n times md. Okay, tensor product expand very fast. And definitely, I can also write this as this column form. V0, Vn minus 1, tensor product W0, Wm minus 1. Is that okay? But how do I do the multiplication? This is what you need to learn, and trust me. I'll put V0 here, and then put the whole thing here, W0, Wm minus 1. Vn minus 1, W0, Wm minus 1. So for each of the elements, I just put the whole thing into there. And I do multiplication and take away the bracket. So this is equals to, can someone tell me what is this? The first one is what? V0, W0, right? And dot, 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 V0, Wm minus 1, dot, 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 Vn minus 1, W0, dot, 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 Vn minus 1, Wm minus 1. Is this also n times n? N times n dimension, right? This one refers to which basis? E0, F0, right? This one refers to E0, F, M minus 1. Yeah, the last one, yeah. And this one is, what is this? Say it. E, n minus 1, F, M minus 1. Right? A lot of math, but really doesn't matter. The point is I want to show even for such a complicated case, you understand very well. First of all, tensor product is just a permutation. You have so many bases, I just permutate them. And just like regular distribution law in addition and multiplication. Second thing, you can write in the column form, right? Okay, you are not going to use this in quantum computing because it is easy. Quantum computing, you only have 2 qubits. Now, of course, if you have many qubits already, you have this also. I cannot say that, but usually not that complicated. Okay? So let's look at an example again, right? This is a real example. I mean, more fundamental example. So I have a C2 space. I have a C2 Hilbert space. So because of this, right, I have 2 vectors, which is F equals to x1, x2. What does it mean? It means I have x1, 0 plus x2, 1, right? And I also have another space. Just an other C2. I have F2 equals to Y1, Y2, which means this is equal to Y1, 0 plus Y2, 1, right? And I can even label it, this is the first qubit, this is the second qubit, if that confuses you, okay? So let's find the tensor product. Okay? The first method is this. Just use the matrix multiplication. F1 tensor product F2 equals to x1, x2 tensor product y1, y2. Okay, so how do you do it? Why don't you try to do it? I will do it here. As I said, I'm going to put x here, y1, y2, x2, y1, y2. So this equal to what? x1, y1, x1, y2, x2, y1, x2, y2. Do you agree? And each of these referring to what? 0, 0, 0, 1, 1, 0, and 1, 1. Okay, make sense? So that's a way. This is method 1. But we can use the traditional method also, method 2. Then it is not, we just use F1 tensor product F2 equals to x1 0 plus x2 1. I skip the subscript. The whole thing tensor product y1 0 plus y2 1. I skip the subscript also. Then do distribution law, right? So what do we get? x1 y1 0 0. x1 y2 0 1. x2 y1 1 0. x2 y2 1 1. Is this okay? x1 times y1 0 tensor product 0. x1 times y2 0 tensor product 1. x2 y1 1 tensor product 0. x2 y2 1 tensor product 1. Right? If you write in the column form, you see that they are exactly the same. Refer to here. Same. Right? Is it same? x1 y1 for 0 0. x1 y2 for 0 1. x2 y1 for 1 0. x2 y2 for 1 1. Okay, so very easy, right? Tensor product should be very easy. Don't make mistake, okay? Any questions? Okay, so we know how to do the tensor products of the vector from a lower dimension to higher dimension. How about the matrix, the operation? How do we do that? Again, it is very